for machine learning is tomorrow. Okay, so in total 10 questions, 5 questions MCQ, 4 questions numerical based calculation, numerical based, and the last one question is coding. Okay, and coding question where you have been asked to complete the function. Okay, so this is the overall structure for the midterm exam, total 90 minutes. Along the way, once I review the topic, I will give some hints what type of questions we'll be asking. Sorry. Apart from this, today's quiz is the quiz 5. This is the final quiz before the midterm, because after midterm you have again a 5 more quiz. Okay. And in today's quiz, we have structured in a such a way that you will get the structure of the today's quiz is same as the midterm exam. Okay, so don't forget to attempt the quiz 5, which is scheduled today from 10:15 to 11 o'clock. Okay, so let's begin for the reviewing the topics that we have learned so far. So this is a machine learning, and machine learning categorized into the 2 categories, which is supervised and unsupervised. Unsupervised. Supervised, where we are giving input as well as output to the machine, and machine will build the model based on the historical data and produces the output. In unsupervised learning, we are only feeding the input, building the model, and the model will give us the output. So supervised learning algorithm, there are multiple algorithms available under this category, but I'm listing here only those algorithms that we have learned. Okay, linear regression, then logistic regression, then KNN, K nearest neighbor, and decision tree. All these are the supervised machine learning algorithm. Under unsupervised learning, you will going to learn about the clustering and the PCA. In second half of this trimester, it means after midterm, you will learn few more algorithm under this category, which is SVM. And yeah, I think SVM, and then this PCA under unsupervised learning that you will learn after the midterm. Okay. So let's first start with the linear regression. Linear regression. Linear regression is an algorithm that we can use to predict the outcome, right? But which type of outcome? Where you have a numerical variable, or the numerical, I can say the feature. I mean to say, if you want to predict the housing price, which is the housing price is a numerical variable. So in that case, you can use the linear regression, the salary of the employee. Such a type of problem statement you can solve by using the linear regression. So basically what linear regression does, I'm taking only 2 variables. Suppose here number of bedrooms, and here the price of the house. Okay. Again, linear regression is categorized into the 2 categories: simple linear regression, and multiple linear regression. Okay, multiple linear regression. Simple linear regression means where you are using only one input feature. Multiple linear regression where you are going to use multiple input features. The example that I am explaining, I'm only considering one input feature. Sorry. one input feature which is the number of bedrooms and one output feature which is the price. So based on the value, your data looks like this. If you plot this 2D graph, your data may looks like this, and you are trying to find the best fit line. Okay. In a linear regression, you are trying to find the best fit line, and the equation of this best fit line is y is equal to wx plus b. W is the weight and b is the bias. Okay. So this is basically by using this equation, you will predict the outcome. So you are trying to find the best fit line. So how we will get this best fit line? By minimizing this error. Because the dots you are seeing, these are the actual values, and all the points on this line is called as the predicted value. If you find the distance from this actual value to the predicted value, all these are the error terms. Okay. And we are trying to minimize this error term, so we will get the best fit line. Okay. The error terms, the error or the loss in linear regression, or it is also called as the cost, loss, or the error in a linear regression, is calculated by actual value minus predicted value, which is y hat whole square. But there are n number of points, so we need to take a summation of I is equals to 1 to n. So this is basically a loss function for linear regression. So we want to minimize this loss function, so we will get the best fit line, and for the best fit line we should get the best parameter as well. To get the best parameter, we need to use the gradient descent algorithm, okay, where we are trying to minimize the error and get the best parameter. Everyone knows that the gradient descent will give us this convex convex curve, which is parameter here, parameter which can be W or bias versus your loss. You will get this curve. So we want to reach over here. This point is called as a global minima. Global minima. This point is called as a global minima, and to go down step by step, this step has been taken. This is called as a learning rate, okay? Alpha, which is called as the learning rate. How big is your step? That is called as the learning rate. And the formula for this gradient descent is you need to take a partial derivative of weight with respect to the partial derivative of loss. The partial derivative of loss with respect to parameter, first time W, and also you need to calculate partial derivative of loss with respect to bias. Okay. Once you calculate this, you need to update your parameters, which is W and the bias. So you will get W new and bias new. So to get the new parameter, you need to subtract this gradient from the old value. So W old minus this parameter gradient of partial derivative of loss with respect to W, and you need to also specify the learning rate, like what is the size of the learning rate, means what is the size of this step. So you need to mention that. So it will be times alpha. Similarly, for bias, old bias minus, you need to subtract the gradient partial derivative of loss with respect to bias times learning rate. Okay. So in exam, we may ask you to calculate this new weight, okay, new weight and new bias. So for this equation is like y is equal to wx plus b. So w may be given, bias may be given. You need to calculate this y, and this formula will be given, and learning rate will be also given. You need to calculate the new parameter w new and the new bias. So you need to calculate the new parameter after the first iteration or the second iteration. So the instruction will be given clearly. Okay. So there may be a problem based on this calculation. Okay. So until now that we have seen this linear regression, and where we can use the linear regression where we have to predict the numerical value. In terms of multiple linear regression, only the just formula will change. Y is equals to W1 x1 plus W2 x2 plus W3 x3 plus up to Wn xn plus bias. This will be the formula when you have a multiple input features. Okay. This is for the linear regression. Yeah. Apart from this, the performance measure, I would say the R square and adjusted R square along with the loss function. These are the two metric also can be used as a performance metric for a linear regression. Loss is there, definitely loss is there, which is also called as the MSE, mean squared error, right? So loss will be there along with that R square and adjusted R square. So R square will increase. R square will increase if you are adding a multiple input feature. Suppose first time you have taken a first input feature, then R square something suppose 30, and if you have added another input feature, your R square will increase. If you have added another input feature, your R square will increase. But adjusted R square will increase only when if the added input feature is adding a contribution to the prediction. Means, for example, if really, suppose you are predicting the cells and you have given three uh, three ways to do the marketing. For example, the newspaper, TV sales, and the what was the radio. Okay. So if you first time if you are adding a TV as a parameter, your R square value something 40. Then next time you have added one more parameter radio, your R square value maybe reach to 60. And when you are you have added the newspaper as an input parameter, your value reach to 65. Means, for example, this TV and the radio is having a more importance than the news. So, but R square, regardless of the importance of the input feature, the R square will increase. But adjusted R square will only increase when the input feature is really contributing towards the prediction. Okay. So that's why this R square and adjusted R square is also another performance measure. The next algorithm that we have learned, the logistic regression. Logistic regression. Logistic regression mostly used for the class as a classification. It's a classification algorithm. Classification algorithm. When you have to predict the categorical variable or categorical feature, then you can use the logistic regression. Logistic regression most commonly used for a binary classification. What is meant by binary classification? It means when you have to predict only binary outcome. For example, email spam or not spam. Second, whether the credit card transaction is a fraud or not. Such a type of problem statement you can solve by using the logistic regression. In a logistic regression, the function that we are using, which is called as the sigmoid function. This is called as a sigmoid function. And the formula for this is 1 upon 1 plus e power minus z. And this z is nothing but the equation of your linear regression, which is wx plus b. Okay. This is a logistic regression formula. So even though in a logistic regression, the value, the W value and the bias value will be given, we may ask you to find out this, the outcome of this particular problem. Means it, I mean to say the W will be given, bias will be given. You need to find out this sigmoid. The sigmoid will give you the probability. Based on the probability, you need to predict the outcome, whether it is S or no. So there might be a problem based on this logistic regression also. Okay. And in a logistic regression, the cost function is indicated with minus 1 upon m y log of y hat plus 1 minus y log of 1 minus y hat. So this is a loss or a cost function for the logistic regression, as there are n number of data points. So I is equals to 1 to m, because we have taken m over here. So m. So this is the cost function for a logistic regression. And to minimize this cost function, we also use a gradient descent in a logistic regression. If we, in a logistic regression, if we use suppose if you use the linear MSE as a loss function, then we will end up with this kind of curve. So we can stuck into the local minima. We never reach to this global minima. So that's the problem, that we are not using. We cannot directly use the linear regression loss function for the logistic regression. So that's why we are using this particular loss function for the logistic regression. And if you draw this loss versus parameter, you will again get this convex curve, and we want to reach at this point, which is a global minima. And again, you need to go step by step over here. And this step is called as a learning rate. Learning rate. What is the formula? What is the formula for the gradient of the logistic regression? Anyone? So for a logistic regression, again, we need to calculate the updated weight and updated bias, that you will get it by W new is equals to W old minus alpha times. You need to subtract the gradient, that partial derivative of loss with respect to partial derivative of loss with respect to W. Similarly, for bias, the W, Similarly, for bias new is equal to, you need to subtract from the old bias the learning rate times the partial derivative of loss with respect to bias. But in a logistic regression, the partial derivative of loss with respect to W is equals to A minus Y times X, which is your A is nothing but the predicted Y. You can say it is A is equal to Y hat. Only the notation is different in a logistic regression. And partial derivative of loss with respect to bias is nothing but the Y hat minus Y, which is equals to A minus Y. Here also I will rewrite this. Y hat minus Y times X, which is equals to A minus Y times X. So this is the gradient descent for the logistic regression. Any questions so far before I move forward for the new algorithm, which is KNN? Any questions so far? Okay. As we were talking about the logistic regression, I will also discuss the performance parameters for the classification problem. For the classification problem, we are using confusion matrix. Confusion matrix. If you remember, then it has 4 parameters: true, positive, false positive, false negative, and true negative. In this case, actual will be here. and predicted will be here 1 0 1 0. Apart from this, if you see the matrix like this, true positive, false negative, and true negative. So you don't have to confuse. In that case, your actual value will be here 1 0 and the predicted will be here 1 0. So you have to decide on which axis you want to take actual and which axis you want to take a predicted. But I will suggest this on the row side, always take actual, and the column side, always take a predicted one. True positive means it's actually positive and predicted as a positive. For example, the patient is having a cancer and predicted as a cancer. This is called as a true positive. Then false positive, the patient is not having a cancer, but model predicted as a cancer. Patient is not having a cancer, but model predicted as a cancer. It is called as a false positive. Then false negative, actually having cancer, but model predicted as a no cancer. This is a false negative. Patient is actually having a cancer, but model predicted as a no cancer. It is called as a false negative. And this true negative means actually no cancer and predicted as a no cancer, which is true negative. False positive is a type 1 error. And this false negative is a type 2 error. And based on the problem statement, you have to decide which error is most important. As you are working in a healthcare, just now the example that we have seen, the cancerous one, in that case, false negative type 2 is more important than the type 1. So we will try to minimize the false negative when we build the model. Okay. Apart from this, accuracy is nothing but accuracy can be calculated by true positive plus true negative divided by true positive plus false negative plus true negative. You will get the accuracy. But accuracy is not the correct performance measure when your data is imbalanced. When your data is imbalanced, then accuracy is not a performance measure. Why? Let's take an example, the same cancer example. 95% of the data is no cancer, means zero category. And only 5% of the data is having the cancer, and which is the category 1. You are training a model on such a biased data, means the maximum 95% of the data you are feeding to the model that no cancer, no cancer, no cancer. There are only few 5% of the observation that belongs to the cancer. So model will learn too much on the no cancer observation. So whenever you try to predict something on a new observation or a new data, your model will always give you the result 0, means no cancer. Even though for such a model you will get the accuracy 100%, that model is also useless model, because you build a model on such a biased data. Your model always giving the biased result, even though it is giving you 100% accuracy. So that's why we need to consider the other factors, which is called as the recall, precision, and F1 score. If you use F1 score, which is already a harmonic mean of this recall and precision, which is 2 times recall and precision divided by recall plus precision. So whenever a data set is imbalanced, recommended to check the F1 score, because this is already considering the recall and precision. If you build a model on such a data where you are getting 100% accuracy on a training data, but very poor accuracy on a testing data, that model is called as a overfit model. This is called as the overfitting. Again, I will explain the scenario for overfitting, underfitting, and the generalized model. So suppose you want to find this best fit line and your data points are here. And this is your testing data points, suppose. So where your training error is high. This is your training error is high, means high bias. High bias. And testing error is also high. Test error is also high. This is called as a high variance. High variance. Or even here you can also consider the low variance, even though training error is lower as compared to the testing error is lower as compared to the training error, low variance. Both the cases you can consider over here. Okay. When you have a high bias and high variance, this condition is called as a underfitting. Underfitting. It means that your model is not performing well on a training data. So definitely it won't perform well on a unseen data. For example, the model accuracy on a training data, the model accuracy, suppose you are getting 40% and testing data accuracy is 30%, then you can say the model is underfit, not performing well on a trained data, so definitely it won't perform well on a testing data. This condition is called as the underfitting. The another condition where suppose these are your data points. The model will try to find all the data points. So your best fit line will be like this. So this condition is called as a overfitting, where bias, low bias, and high variance. High variance. Low bias means low training error. High bias means high testing error. Your testing data points are here. And on the line, all the training data points, your testing data points are here. So there is zero error for training data and the high error for testing data. This condition is called as a overfitting, means model perform well on a seen data but unable to perform well on a unseen data. This is called as a overfitting. Overfitting. And the third scenario where training data is like this, testing data is also like this. It means that model perform well on a seen data as well as unseen data. Here you can see the training accuracy around 95% and testing accuracy around 92%. So this model is called as a generalized model or the best model, and that model you can use it for your deployment. Okay, this condition is called as overfitting, underfitting, and the generalized model. So far, any question before I move to the Canon? No. The Yes, if you go to the industry, then you need to use this region lasso regularization. But as a part of the exam, I haven't covered the region lasso regularization. Okay. So yes, this regularization techniques. Thanks for asking this question. This regularization technique will help you to avoid the overfitting by penalizing the parameters. Okay. Now next, KNN. KNN also used for the regression as well as classification. Classification again, when you have to predict the continuous value, and when you have to predict the categorical value, then you can use for classification. Okay, so for a class KNN, K stands for K nearest neighbor. So K value can be anything. Initially, we don't know. So there is a standard that you can use. K is equal to square root of n. N is the number of observations. Okay. So suppose K value is equals to 3. It means that suppose there are data points like this. And another data points like this. And you need to find the outcome for this. You need to find the outcome for this, whether this is from, suppose this is class 1 and this is class 0. Okay. So you need to find the outcome for this. So by using the KNN algorithm, you will find the distance from this new data point, which is this one, and you need to find the distance to the all the available observations, all the data points. You need to find the distance. Okay. And based on the shortest distance, you need to take the nearest three values. Suppose nearer is this one, and this one. Okay. Suppose these are the nearest three value. We are considering, suppose this is nearest value, this is nearest value, and this is nearest value. Okay. Here. So in the circle of three nearest neighbor, the two neighbors fall into the one category and only one neighbor fall into the zero category. So based on the majority of voting, the outcome for this new data will be 1, class 1. So it works in that way. But for the for specifically for this KNN algorithm, you need to standardize the data. Basically, not only for the KNN algorithm, for all the machine learning algorithm, you need to standardize your data. Means because if there are a few variables which is having a very high value and a few variable which is having a very low value, so the high valued variable will dominate the other variables or other feature. So that's the reason you need to standardize or normalize your data set, and it's applicable to all the machine learning algorithms. Okay. You need to standardize your data set. If there is any categorical variable available, you need to convert into the numerical format. Okay, because all our machine learning algorithms is having a numerical calculation in the background, right? So we need all the numerical values. Even though if your data set is having a categorical variable, you need to convert into the numerical format by using the one hot encoding or label encoding. There are few more ways to you can do it, but this is commonly used, one hot encoding and label encoding. One hot encoding means whatever the categories are available, it will create the separate column for each category. For example, if you have categories male and female, so it will create the one first column, suppose column 1, which is having a female and male. So after doing the one hot encoding, it will create the first column, this is like this, and second column like this. So if in the first observation female is present, then it will mark as 1, 0. In the second observation male is female, then it will mark as like this, like this. So wherever this category is available, it will mark as a 1, the rest all 0. The second way, the label encoding, it will assign the numbers based on the alphabetical order. For example, male and female. The female will occur first in alphabetical order. So the value for female will be 1 and for male is 2. So it will assign the values in a such a way that this is called as the one hot encoding or the label encoding. So KNN and if you talk about the regression problem for the KNN, instead of majority voting, so for example here, these are the three nearest data points. If it is a classification regression problem, this data point must have some numerical value as the outcome. This is also numerical value. This is also numerical value. So the algorithm will take an average of all this numerical value and it will give it as a prediction for the new data. So if it is a classification problem, then it will take a mode operation, which is a voting, right? Mode operation. This is called as a voting. Suppose in this k is equals to 3, if category 2 is occurring one time, and the category, suppose instead of category, I will mark it as a star. This star is occurring one time, and this red star is occurring 2 times. Then definitely we will go for majority voting. This operation is called as a mode operation. Okay. So we are going, the outcome will be definitely the class 2. But in case of regression, we will use mean or average to find the prediction. Suppose this value is having the value 3.2, 2.8, 3.1. So it will take the average, which is like 3.2 plus 2.8 plus 3.1 divided by 3. That will be your prediction for the new data point in a regression problem. Any questions so far? So I will open this slide for the Canon. As 3 major steps, calculate a distance. And here we are using the Euclidean distance. All of you know how to calculate the Euclidean distance, which is the square root of x1 minus x0 whole square plus y1 minus y0 whole square. Then, based on the distance, get the nearest neighbors and make the prediction. Similar, the same example that we have seen. When k is equals to 3, so there are 3 data points inside the circle. So definitely this E prediction will be class B. But when k is equals to 6, we are taking a more data points into the consideration. Now we have a 4 data points from class A and only 2 data points from class B. So in that case, when k is equals to 6, then the prediction will be class A. So this was the example. To calculate the distance, we need to take a square root of, subtract the respective data points, 35 minus 22, 35 minus 50, and number of credits 3 minus 2 on all whole square. And you need to take a square root of it. Okay. Yes, in this example, if you see, we have used the distance metric to calculate the distance, but this income variable or the feature is having a very high value as compared to the age and the number of credit cards. So if we build a model on such a data, our model, the income variable, the particular income feature will dominate the other feature and model will be biased towards the income feature. So we need to standardize our data set. Now here we have standardize our data set. There are many ways to do the standardization. Min, max scalar, standard scalar, average scalar. So you can use any method. And as I mentioned, if it is a categorical variable, you need to convert into the numerical format. Here, one hot encoding is used. So 3 categories, Dover, Newton, and Queenstown. So by using the one hot encoding, internally it will create the 3 different columns for each category. Distance, Euclidean distance, you can use any distance, but most commonly used distance metric is the Euclidean distance, Minkowski distance, and the city block distance. K&N variations, yes, this part I didn't explain. Value of k. If k value is equals to 1, it means your model will learn too much from the training data. When k is equals to 1, that there can be a case for overfitting. Okay. If k is equals to n, means all the data points into the only one cluster, one cluster. So this will be a case, can be a case of underfitting. I already explained how can be a case of overfitting and underfitting. Because in this case, we are putting all the data points, all the observation into the one cluster. Instead of giving a more importance to the nearest neighbor, it will go for the majority for the whole class. Okay, it won't give the importance to the nearest neighbor, so it will give us the wrong prediction. So this is called as the underfitting, where model unable to predict well for the seen data as well as unseen data. When k is equals to 1, it may perform well on a seen data but unable to perform well on a unseen data. Yes, how to choose k? So the simple approach to choose the k value is k is equals to square root of n. Else we have covered almost. Here are the few advantages and disadvantages for the KNN. Okay, and this is a simple implementation of KNN by using the sklearn library. Before I move forward, any question? Any questions so far? Okay, if no question, then I will cover the last algorithm, which is a decision tree. Again, decision tree is an algorithm that you can use for both regression as well as classification problem. But as a part of our curriculum, we have covered the cart decision tree. Here there are the few advantages of this decision tree, which you can visually see the output. This is the main advantage, where provides a visual intuitive output, so it's easy to understand and interpret as well. And outlier treatment is not needed because we are splitting the data on the left tree and the right tree based on the Gini. So really the outlier treatment is not needed for such a problem, for such a algorithm. But the disadvantage is that the classification tree may be biased trees if some classes dominate. So that will be a disadvantage. So whenever we build a decision tree, the recommendation will be to make it all the categories must be balanced. So you have to use a balanced data set. If the data set is imbalanced, you can use some technique called SMOT, upsampling, downsampling, to make the data set balanced. Okay, so you can use all these techniques to make your data set balanced. And once your data set is balanced, then you can build the machine learning algorithm. Specifically for a decision tree, you cannot build the model on a biased data set, means imbalanced data set. It will your model will, your tree will be biased towards the only one category. So recommended to use the upsampling or downsampling to make the dataset balance. There are a few issues with this decision tree, means impurity based criteria. You have to select the impurity based criteria, which criteria you are going to use, or which criteria will be the best for that particular data set. So there are two ways to measure the impurity, Gini and entropy. Information gain, which is you can derive from the entropy. Statistical measure of association. You can consider MSE for the regression problem, mean squared error for the regression problem. For classification problem, you can use Gini or entropy. Uh, for CART algorithm, there is only binary split. Means if it is a root node, it is only if it is having only the two childs, which is called as a binary split. But there are, in a decision tree, there are other algorithms that prefer the multi-way split. Means it can have more than two split as well. And finding the right size, which is again another issue for a decision tree. So stopping criteria, we must decide, or we must give them a proper, what could be the size of the leaf node. Then pre-pruning, this is called as a pre-pruning or post-pruning to find the right size of the tree. Yeah, as I mentioned, there are a few algorithms comes under the decision tree. This chart, chi-squared automatic detection, interaction detector. This is one of the algorithm. And this is a non-binary decision tree, means it is a multi-way decision tree. One root node can have a multiple childs, means multiple child nodes. Okay. Classification and regression tree that we have covered, which is only have a binary decision tree, which splits a single variable at each node into the two subnodes. Okay. CART algorithm recursively goes through an exhaustive search of all the variables and split values to find the optimal splitting rule for each node. Apart from this, IDT, C4.5, C5.0, these are the also decision tree algorithm, and it is based on the information entropy. Now we are talking about the decision tree, which is a CART, classification and regression tree. If you remember correctly, in a decision tree, we need to find out the feature which help us to split the tree. We need to find out the base feature. To find out the base feature, we need to find out the Gini for all the feature or entropy for all the feature. Where we get the lowest entropy or lowest Gini, we will consider that feature as a root node. And based on the condition, we will get the left samples and the right samples. Okay. So in this example, suppose we got the lowest Gini for refund, and then we it converted into the two categories, yes or no. When the refund, if you see over here, refund S and refund S, that time this stack, the target variable, all the values are no. Means this is called as a homogeneous node. So no need to further divide that node. So this is called as a leaf node. But if you on the no side, there are no side, no side, this is no. But for no also there is a S. So this can be again categorized, subcategorized. So we have taken the next feature, which is marital status. And this marital status again categorized into the two, married, single or divorce. One for the category married, all the outcome labels are no. But for the category single and divorce, there are a mixed outcome. So we need to take another feature that will help us to make the nodes homogeneous. So tax 80K, if you check this data less than 80K, all the homogeneous node means it belongs to no, and all the income which is greater than equal to 80K, all for this particular condition, this tax event is having the value S. Okay. So based on this tree, if you pass the new condition or the new data, your model will try to predict. Suppose refund no, marital status single, and taxable income 70K, means which is less than 80K. So you can see what is the outcome for that particular new data will be no. So the outcome or the prediction will be no based on this tree. This tree is called as a Hunt tree. We will directly jump to the calculation. Gini index. The Gini can be calculated by using this probability, or we call it as the relative frequency of that particular class. It's maximum when records are equally distributed. Gini will be maximum when records are equally distributed. For example, you see there are two classes C1, C2. The records are equally distributed. Gini is 0.5. But when it is only one category, means suppose the one category C1 is 0 and C2 is having all the observation, in that case Gini is 0. So we want to reduce the impurity, so we are looking at the lowest value of Gini. If it is a higher Gini, means that particular node is impure node. So Gini, here you can see, I will take the example directly. You can calculate the Gini like this. Overall, You see, this is a root node, which is the root node is having a 10 observations, and in that 10 observation, 4 are true. So definitely the false observations will be 6, right? Out of these 10 observations, if you see over here, you can see 1, 2, 3, 4. Only 4 observations are true, which is means for 1. And false means 0. There are 6 observations. So we have to consider the first feature as a gender. We gender male and female. For male, we have 6 observations, and for female, we have 4 observations, and in total 10 observations, which is the root node, right? Now, out of these 6 observations, how many are true? 3 true. And out of these 4 observations, 4 data points, how many are true? Only 1 is true. So yes, same calculate the Gini. This is Gini for overall, means for Gini for this root node, 1 minus each category 4. The true is occurring 4 times. So 4 out of 10 whole square plus 6 out of 10 whole square. This will give you the Gini for overall. For male, 3 on 6 and 3 on 6, which is 3 true and 3 negative, right? 3 false. So 3 over 6 whole square, 3 over 6 whole square. For female, 1 over 4 and 3 over 4. And when you calculated the Gini for gender, we have calculated for male and female. Now you have to calculate for that particular feature, gender. So you need to take a weighted average. So 6 on 10.5, which is for male, 4 on 10.0.375, which is for female. So you will get the Gini for gender. And how will you get the Gini gain? Gini overall minus Gini gender, or that particular feature will give you the Gini gain. We are looking at the lowest value of Gini. Lower the Gini, better the feature. Or in terms of gain, higher the gain, better the feature. Okay. So when you are looking at the gain, it should be higher. If you are looking at the Gini, it should be lower, because Gini is measuring the impurity of a node, and gain is measuring the reduction in impurity. Okay. So similarly, here we have calculated for this employee feature, and this is for the age feature. If you compare the Gini gain 0.08, 0.00, and 0.03, the higher Gini gain is for the age factor. So we will consider the root node as the age, and then we can split. But as in the under the age, we have multiple values. So which value we should select to split the node? So we have taken 20, there are 4 values, 22, 23, 24, and 25. We have taken all the condition, and for all the condition, we have checked Gini gain on Gini. So for higher Gini gain is only for less than equal to 25. So that's why we have considered this condition. But this is not the fix that you can consider all the values. Suppose in this age, you have value 22, 23, 24, 25. So we have checked the condition for all the values. But the common practice is to take the average, means 22 plus 23 divided by 2. What will be the average? Take that as a split. The next time, this 23 plus 24 by 2. If whatever the values, take that as a split. So you can use this strategy to find the proper splitting condition. Okay. This is also correct. This is also correct, the average one, but the most common practice is by taking the average. Similarly, entropy. In entropy, we are using a log function, log base 2. So this also measure the impurity in a node. Again, it is maximum when it is equally distributed. If it is a minimum, only the one category is occurring. Information gain is nothing but the entropy of parent node minus entropy of the child node. Same, you can see we have calculated the entropy for the parent node over here. So the probability of positive will be 4. The probability for true is 4 by 10, and probability for false is 6 by 10. So you can see over here minus 4 upon 10 log 2, 4/10 plus 6/10 log to 6/10. So you will get the, sorry, here this should be entropy. Entropy. Then similarly, you need to find the entropy for male, entropy for female, and then entropy for gender, which is the weighted average. So now we got the entropy for gender, and this is the information gain, which is a Gini over. This is, I think I have taken. This is entropy. Should be entropy, and this should be entropy. Entropy for overall and entropy for gender. So you need to take this minus this one. You will get the information gain 0.047. Higher the information gain, better the feature. Lower the entropy, better the feature. If you are looking at the entropy, it should be lower. If you are looking at the information gain, it should be higher. Similarly, you need to calculate for the other feature, which is occupation, and here the age. And this is a simple model that we have built by on the IRIS dataset, where we have a 3 categories: setosa, versicolor, and virginica, and 4 input features: sepal length, sepal width, petal length, and petal width. I will directly jump to the here tree that we got it. So you can see the first input feature, that is base to split, is petal width, and the condition is less than equal to 0.8, 0.8. For this, Gini is 0.66, and in total we have a 120 observations, okay, or 120 data points. In this 120 data points, 43 belongs to which category? Which category we are having? Setosa, versicolor, and virginica in the same order. So there are 3 categories and these many observations. Now we are splitting based on this condition. If the petal width less than equal to 0.8, it will go this side. If greater, then it will go this side. But if you see here, Gini 0, 0 means it is a pure node. Gini 0 means pure node. All the observations belong to the one class only. The samples 43. And if you see the value, all the 43s belong to the Setosa categories. Say 43, 0, 0. So this category is 0, this category is 0. So definitely all the classes belong to this category, Setosa. Now out of 120 observation, 43 observations here. So remaining observation will go this side. That is a 77. Again, you need to find the best feature based on the Gini. Lowest Gini is for the petal width. Again, condition is 1.7. If less than less than equal to 1.7, it will go this way, or greater, it will go this way. Again, you see on the right side, Gini is 0. The samples 37. And if you check their categories, all belong to the one class, which is Virginica. Now this is a homogeneous node. No need to further split this node. If it is a leaf node, homogeneous node, no need to split further again. But on the left side, again 40 observations. Again, we have taken the same petal width, petal length, condition less than equal to 0.5. And now you can see there are 2 categories, 38 and 2 categories, but 38 belongs to the one class and the 2 observation belongs to the one class. So as this is not the homogeneous node, but most of the category belongs to the versicolor, which is 38. So the class label is a versicolor because maximum categories belongs to that particular class. But again, based on the condition, we are dividing this. If it is less than equal to 0.5, less than equal to 5, then it will fall onto the left side, otherwise right side. Now Gini 0 means the pure node, homogeneous node. 37 observation, all the 37 observation belong to the only one category is versicolor. On the right side, again, because this is not the pure node, we need to further divide it and check the base parameter to split. Again, sepal length condition is this one. Now number of samples 3. And in these 3 samples, 1 belongs to the versicolor and 2 observation belongs to the virginica. So we are based on the condition, we are again dividing this way and this way. Now impurity 0, 0. Number of samples 2, number of samples 1. This is versicolor and this is virginica. If you check all the leaf node, these are the leaf node. all the Gini is 0. Gini is 0 and all the nodes are the homogeneous node. Homogeneous node means it's falling into the only one category. As this is a very small data set, so you are able to see the tree. If your data set is too large, means having billions of observations, in that case you cannot really visually see the tree because it is going very longer and longer, right? So but growing the tree until here is not also recommended, because sometimes if you grow the tree longer and longer, the model may overfit. So for that purpose, you need to specify the number of observations to consider it as a leaf node, or number of observation to split the features. If suppose there should be 100 observations for the maximum, for 100 observations, we can give that value as a feature value. Means if there is a value greater than or equal to 100, then and then only you can split the variables. If the leaf node value is suppose 50, if the value 50 or less than 50, then it is considered as a leaf node, then you cannot further divide. Okay. But you might be wondering, if we are not growing the tree longer and longer, then how can we predict it, the outcome? Sorry. How can we predict the outcome? Suppose if I do not, let's take an example where I can see I do not want to further divide this, because I reach the condition where the number of observation for leaf node is equals to 3. Okay, samples is 3. Now I cannot further divide. So I cannot take this into the consideration. So this will be my leaf node. But in that case, based on the majority, as this class is occurring maximum times, so the outcome will be Virginica. Okay, this will become my leaf node. Okay, this is decision tree. And yes, again, as I mentioned, for classification problem, confusion matrix is a performance measure. This is a classification report where you can see the precision, recall, and F1 score for each category. And this is the accuracy, 0.90. Accuracy is good. As you see, F1 score is towards 1. So the model is the best model, because if you see the number of categories, it is also balanced. As this was a balanced data set, we got the best result. Any questions so far? And these are the hyperparameters criteria. Which criteria you can use? Maximum depth, minimum sample split, minimum sample leaf, maximum feature. So you can use hyperparameter. You can use a grid search CV algorithm to do the hyperparameter tuning. Means, for example, for criteria, we have two values, which is Gini and entropy. For maximum depth, we don't know what could be the best value for the maximum depth. Okay, max depth, you can pass the, suppose if I want to pass the value, for example, maximum depth until 5, 7, 9, 11. These are the values I want to try. And then minimum sample split, mean sample split. It means that what should be the minimum number of samples will be there to split the tree. So I will give suppose 50, 60, 65, 70. If there are these many options, I want to hypertune. And maximum features to split the tree again. Max features. Maximum features, suppose 3 or 5 features. So these are the parameters you can hyper tune by using the grid search CV. You can pass all these parameters to the grid search CV. The grid search CV try all the possible combinations. How many combinations will be possible here? For criteria 2, for maximum depth 4, and for minimum sample split 4, and maximum features 2. So if you do the multiplication, that many number of different combinations possible. Your grid search CV will run the decision tree card algorithm on all these different combination and will give you the best combination where we are getting the best result. Okay, and this combination you can try by using this grid search CV. So this is the hyperparameter you can tune by using this grid search CV algorithm. So there are 64 different combinations, right? Yes. Any questions so far? Yeah, so questions on a decision tree that I will tell you. We may ask you to find out the Gini or entropy. And based on the Gini or entropy, we may ask you to find the outcome of that particular node or that particular observation. Okay. All the values, suppose for example, the table like this will be given. We may ask you to find the entropy for any particular feature or the Gini for that any particular feature. Okay, all the formulas will be given, data will be given. You need to do the all the calculations. Okay, this is for the decision tree. And for the KNN also, the K value will be given, the features will be given. We will ask you to find out the outcome for the input feature based on the K value. Suppose K is equal to 3, and if we are given all the input feature, what will be the outcome for that newly given observation? So whatever the calculations available in your slides, please take a look on this. I may ask you the similar type of calculations or the similar type of example in the midterm exam. Okay. The structure of the today's quiz is same as your midterm exam on tomorrow. So you will get to know that what type of questions I will be asking and all. Any questions so far? We have only 7 minutes now. Do we need to know about the K-fold cross validation as a part of exam? No, not really, because because this comes under the coding part, and in a coding, I'm just asking you to define the code. The formulas are given. By using the given formulas, you need to just define the functions. Yes, formulas. All the formulas will be given wherever the calculation is required. As you mentioned, the K-fold cross validation, I will just explain what will be the K-fold cross validation. So there are 100, suppose 100 rows available, rows, or it is called as observations. Observations, okay. So all these, and if K-fold, which is CV, cross validation, is equals to 10. This is the common value, the common practice to use 10. It can be 5, it can be 2, it can be 7, anything. But the most commonly valued is 10 for the cross validation. So what will happen in a cross validation, if the CV is equals to 10, all the observation will divide into the 10 buckets. So for example, so this is fold 1, this is fold 2, this is fold 3, 4, 5, 6, 7, 8, 9, and 10. 10 fold. Okay. In the first iteration, all the 9 folds will go through the training. Means we will build the model on first 9 fold and we will give this last fold for testing. Okay. And this is for training. In the second iteration, now we will give this and this. This is for training. This is also for train, and this is for test. Okay. Now we will give this first 8 fold and the last fold for the training and the 9 fold for the testing. Similarly, in each iteration, This fold will go to the testing, remaining will go for training. So likewise, in the 10 iteration, each fold will go through the testing and each fold will go through the training. In this way, we can also avoid the overfitting. Means we can check that the training model itself, how it is performing on the training and testing. So each and every observation will go through the training and testing. Okay, so this is called as a k-fold cross validation. So we are basically building a 10 models on a training data. Suppose here we are having a 100 observation. In a normal practice, we build the model on this 100 observation. If 100 observation is giving for training, we build the model on this. We build or train the model on this 100 observations. So we directly build the model on this 100 observations. So only one model. But rather than building only one model, by using the cross validation technique, we are internally building the 10 model. So basically in each iteration, in the first iteration, all the 9 fold will go to the training and this last fold will go to the testing. Then every iteration, the test fold will change and the remaining fold will go to the training. We are building the 10 different models under this. And at the end, the result that you are getting, it's based on the average value. So because each model, each iteration, each model is giving you the accuracy. So at the end, it is taking the average of it. This is called as the k-fold cross validation. K-fold, the cross validation value is up to you which one you want to take, but the very standard practice is CV is equals to 10. When you hypertune your parameter with the grid search CV, so in an earlier example, if you remember here, not here, we tried a different parameters, like there were 64 different combinations. Along with this, if you use the cross validation, which is equals to 10, then you will get 640 different combinations. So your model will try all these combinations. Out of this 640 combination, it will return only one combination, which is giving us the best result. In the industry, it is highly recommended to use hyperparameter tuning, because you cannot rely on the default value. So to get the best value, you need to hypertune your parameter. Okay, that's it from my side for this week. This is my last lecture because for the machine learning 2 instructor, the first half will be covered by myself, and the second half will be covered by Dr. Zuyan. So from after the midterm, the another faculty will take over. Any questions so far before we begin with the quiz? Because 10:15 there is the quiz, which is quiz 5. Any questions so far? If no question, then you can log into your Moodle pages, respective sectional pages. You can find the quiz 5 over there. Once you finish the quiz, you can end the call. And if you have any questions related to any topic or related to the midterm exam, please reach out to me on Teams, via Teams or emails.